Hello and welcome. This is the next question, question number 3 for AQA's A2 physics. This is section A still? Section B, God's sake. And this is question 3 for June 2015. Okay, so we're given this graph, which is a current time graph for a capacitor discharging through a 150 ohm resistor. Kept trying to stop myself from saying that, thinking I'm not going to say that, and because I was thinking that, I did say it, so well done me. Anyway, so the first question is fairly simple, although you might think, how, if you didn't see this, then obviously you won't get it, it's obvious. Anyway, it says, explain how the initial charge on the capacitor could be determined from the graph of current against time. Okay, now there's only ever going to be three things, okay? It's only going to be one of three, okay? For anything where it's asking you how's it shown on the graph, it's either going to be where the intercepts, the area under the graph, or the gradient, okay? Now, that third one, okay, the gradient, only really applies if it's a linear graph. Now, obviously, this is quite clearly, I mean, maybe you can see it better from the actual online paper, okay, as opposed to my kind of crap drawing of it, okay, but generally, I mean, that's an exponential. Generally, in exponentials, they won't really ask you for the gradient, okay, of, apart from you could say, well, if we're looking at decay, then fair enough, okay, if you're looking at a radioactive decay, then obviously gradient is a decay constant, but seeing as we're not, okay, so maybe that's just shot myself in the foot there. Generally, with exponential graphs, it won't be the gradient, as I say, unless it's the radioactive decay, okay, it won't be asking about the gradient. So therefore, it's either going to be the intercept or the area under the graph, okay. Now, it's not going to be the intercept, because the intercept indicates the initial current, as you can see. This is obviously the time axis, and obviously this is where it's T0 and the initially, okay, that'd be the initial current, so it's not going to be the intercept, okay. I mean, so if you weren't sure, okay, if you didn't see the fact, you didn't think, oh, it might not be, it might still be the gradient, okay, and if we definitely discount the fact it's not going to be the intercept, it's either the gradient or the area under the curve, okay. Now, as I hopefully tried to give you a bit of an insight, it won't really be the gradient, okay, as I say, unless it's asking about radioactive decay and a decay constant, so therefore it must be the area under the curve, and this is backed up by the idea, basic equation, okay. I know this isn't especially a rectangle or a square, okay, but we've got I, we've got T, we want Q, so back AS physics, okay, Q is equal to IT, okay, so therefore if we times this, I by T, we get Q, okay, so the area under the graph, and that's probably a better way of analysing it, okay, but both ways kind of work, okay, so therefore Q is equal to IT, obviously you wouldn't state that, but that just kind of emphasises what I'm saying, but you wouldn't write that in the answer, okay, even though it appears I've done. You just say the area under the graph. You don't need to explain why. It's only worth 1 mark, okay? Even though there's a lot of lines there, don't feel like you have to explain it. I've just done that so you understand where it's come from. So area under the graph. Well, properly speaking, it's the area under the line in the graph, okay? But obviously above the x-axis. But anyway, that's just easier to say. Right, okay, so that's A part 1. A part 2 says the same capacitor is discharged through to the same potential difference, okay, and then discharged through a 300 kilo ohm resistor. Sketch a second graph, okay, on the same axis to show how the current varies with time in this case. Okay, now there's a couple of things. So just to make sure you know what's happening here, it's the same capacitor, so exactly the same. So everything about this capacitor is the same. The rate at which it loses charge, the capacitance of the capacitor, okay, that's exactly the same. The amount of charge it can hold, it's all the same, okay. However, we've basically increased the resistance, okay. We've increased the total resistance in this circuit. It's pretty much what's happened here, okay. And the attempt to do the same thing, okay, you charge it up to the same point, hence it's going to have the same current. Well, actually, no, not the same current. What am I going? Shut up, Will. Yeah, okay, so it's just going through a high, it's just increasing resistance, that's all it's done, okay? Now, how do we know what to draw, okay? So, I think the thing to think is, okay, if it's going through a greater resistor, okay, you could use, again, you could use the idea that V equals IR, okay, and if it's charged to the same potential difference, okay, in other words, V is not going to change, but we quite clearly know it's now going discharging through a much more a higher resistor, okay. Okay, basically we're increasing this resistance value. Okay, so if the potential difference will stay the same, okay, and we know the resistance increases, okay, then the current must decrease, and there's no reason why we can't use this equation to explain that. Okay, but as I say, it's not asking you to explain it; it's just asking you to draw it. So it's worth 3 marks, but I'm just trying to build it up so you know why we're drawing what we're drawing. Okay, so therefore, as I say, the current must be lower. So therefore, whatever graph this is going to look like, okay, and hopefully I'll explain why it does like it does, it's going to be lower than that line. It can't possibly be above that line at any point, okay? Now, we're discharging it, so it doesn't matter what it's going through, okay? If we're discharging the capacitor, it's going to be an exponential graph, okay? So, there's 2 boxes ticked already. We know the line is going to be lower than this, okay? And we know it's going to be an exponential graph, okay? So, therefore, because it's got the same, yeah, so we know that it's going to be an exponential and it's going to be lower than that line, okay? Yeah. Yeah. And because the current is going to be very low anyway, it's not going to be as easy to see as this curve, okay? So it's going to look something like this. So it's going to go very low and you'll continue it on an almost horizontal line, okay, to the end. Now, there's a few points, okay, that I've seen. You probably can't tell from how I've drawn it because it's pretty crap. There's a few points that they require, because obviously you have a proper graph in the exam to draw on, and I kind of, well, I could, but can't bother. Okay, I could draw it properly out, but you know, I'm the one doing this video and I'm doing it for free, so shorthanders can't be bothered. But there's a couple of things that you need to have on it. Okay, so this line, okay, that I've the second line we're drawing on, okay, as I say, it has to be below the original line they've drawn, the one I've drawn in red. Okay, and it specifically says the line must start within the bottom half of the first square. Okay, now I can't say any more than that. Well, obviously I could, but again, can't be bothered. It's just life, it's just how it works, you know. You do a few of these videos, you think, yeah, I'll jump around, I'll point at the camera, I'll pretend to punch the camera at some point, so do check out one of those videos, I can't remember which one it was. Anyway, yeah, so it just has to start within the first square, and the fact that it has to go almost horizontal, okay, for a period of time. Okay, so as long as it obviously doesn't touch the axis, because you can't have minus current, because remember this is a current time graph, and really it's not gonna start going in the opposite direction. Okay, so you can't have the current as negative. Okay, so hopefully you can see why that is. But again, it's worth 3 marks, so hopefully it wasn't too bad. As I say, I assume even if you knew what you were doing, you could easily lose a mark for not having it in the first square. Okay. Now the reason why it's in the first square, okay, the bottom of the first square, is again using this equation. Okay. Now we know it's going through we know it's going through a much higher resistor. Okay, and you're given the exact value. So I've just stated it. Can't remember what it was. Okay, yeah. So it's going through a 300 kilo ohm resistor. Okay, so you could work out. Yeah, basically you have to do a bit of calculation for this, which I can't be bothered. Well, I can't be bothered. I could be, but I'll probably make a bit of a hash of it because I've just thought I might probably need to explain this. Right, goes through the first box. Okay, so you've got to work out what the yeah, I probably will make a bit of a hash of that. you've got to. I'm really sorry. I should have thought this through. We're just doing this question. I thought I won't need to explain that, but I think I probably do. And to be honest, I don't really think I'd be able to. I'm pretty sure. Okay. I mean, I'm sure I put a box above my head saying wouldn't it so easy. But use the current. I'm thinking use the equation I equals I naught times e to the negative t over rc. Okay. And you work out what the, that's it, okay? Or you pick a point, I don't know, you pick a point, obviously, on the original curve, and you use this equation, okay? You sub the point in, use this equation to work out what RC was, okay? And as I say, you know what the resistance is, so you use the point to work out the capacitance, okay? So once you've worked out the capacitance, you therefore need to say, right, well that's the capacitance. We need now to apply this to the new curve, okay? So when you start the new graph, okay, again it's going to be using this equation, and instead of R is 150, it's now going to be 300,000 ohms, okay? Apologise about the noise. So R is going to be 300,000 ohms. You would have worked out what C is from before, okay? So you input the same value for C, and then you just apply this equation, and you should get it within the first square. Yeah, there you go. That's a good explanation. Didn't think I'd manage that, but so that's why you go through the first square. So as I say, I would totally understand if you didn't get that mark. At the end of the day, it's only one mark, and I'm fairly sure if they did an examiner's report, I'm pretty sure they do, but I just not looked for it. I'm pretty sure that'd be a big problem for quite a lot of people. Okay, so hopefully you get that why that is. Okay, probably spent a bit too long answering that. Okay, so this is quite like these kind of questions actually, because it's combining a few things. It's not too difficult. Okay, so for part B, it says in an experiment to show that the capacitor stores energy. Okay. So it's going to be about energy changes, obviously. A student changes the capacitor. Okay, so B is talking about capacitor storing energy. So as I mentioned, it's about conservation of energy and how it changes. Okay, a student changes a capacitor from a battery and then discharges it through a small electric motor. The motor is used to lift a mass vertically. Okay, so quite clearly you can tell there it's talking about energy from a capacitor being used to lift something. Okay, so we're talking about the energy in the capacitor changing to gravitational potential energy. Okay, so we're told a bit about this capacitor. Okay, we've got its capacitance is 0.12 farads. Okay, so C is equal to 0.12 farads. Okay, we're also told, get a copy pen, its charge to its potential difference in, initially V0. Okay, because we might have to use some kind of exponential graph here. Is 9 volts. Okay. And the weight of the mass is 3.5 newtons. Okay, again, we might have to convert that to the mass, or we might not. Okay, so the weight is 3.5 newtons. Okay, calculate the maximum height to which the mass could be raised. Okay, so one of the things we assume in this, and it might ask us that later on, is that we're assuming all the energy from the capacitor is being used to lift it. Okay, so the energy of the capacitor, okay, that at its maximum 9 volts, okay, because I'm assuming it's going to give all of that to lifting this mass. Okay, now if you go to the equation sheet on the equation, you go to the energy of the capacitor. Okay, so we've got either half of QV, half of CV squared, okay, or a half of Q squared over C. Okay, now we've got C and we've got V. Okay, now it doesn't matter if you put it as V0 now, because turns out we're not going to use an exponential graph, but it's always just nice when it says charged to, it's charged to a maximum, and this is its starting potential difference. It's always just nice to prepare yourself and say that's the initial potential difference, so it mentions something else. But it doesn't, so we can just leave it as V. So maybe I confused you. You didn't need to. Okay, so seeing as we've got C and V, I'm going to use that the equation, okay, is E equals a half of CV squared. Okay, and if it's 100% efficient, that's what we're assuming. Okay, all of this energy is transferred to lifting the mass. Okay, and quite clearly it's talking about gravitational potential. Okay, so therefore EP is equal to mg times delta H. Okay, key to remember as well. Now you could go, well, we've got the mass, we've got the weight, so you divide it by g. But you remember W equals mg, so you can just say, you could almost say the potential difference. So gravitational potential and GPE, GPE is the weight times the change in height. Okay, and if it's 100% efficient, the energy of the capacitor, as I say, E equals a half of CV squared. That's the one I've chosen. Okay, now you could work out what Q is from this, but there's no point. Okay, because we've got enough to use the equation. So therefore, you make these two equal to each other and simplify down and rearrange so you can work out what the height ends up being. Okay, now remember you're giving it in meters, so you're giving it answers in meters unless it asks you otherwise. Okay, so a half of CV squared. Okay, so it's a half times 0.12 farads times 9 squared, which is obviously 821, but you leave it as 9 squared. Okay, and that's the energy in the capacitor, so that's equal to the gravitational potential energy which is gained. Okay, which is the weight, which is 3.5 newtons times delta H. Okay, and you just rearrange, okay, to get the change in height as 1.4 meters, and that's the two significant figures. Okay, so that's how you would answer 3B part 1. 3B part 2 was the last little bit of 3, and it's kind of explaining why this would not be the case. This is a maximum height it could reach, but basically the 3B part 2 is saying why would it not reach that height. Okay, now there are two reasons. Okay, so they're both obviously to do with energy loss. Okay, in other words, not all the energy is transferred from this to the gravitational. However, that sounds like there's only one reason there. Okay, well that's correct. However, it's not. I don't think this is being specific enough. It's saying what is the. Although saying that if it was specific enough, it would give it away. Which I guess. I mean, I've not got any problem with that, but I don't think the paper would be too difficult if they did that. Anyway, so you just need to say that yes, there is energy lost. Okay, that is not transferred. Some of it is lost to resistance forces. Basically, what you need to do is two reasons. What are two examples of those resistance forces, and they both therefore have kind of similar explanation. Okay, so one of the explanations is the fact that there's internal resistance in the actual capacitor or motor lifting the weight. Okay, so therefore some of the energy is lost to that. You could also say there's heating in the ropes. Okay, because obviously you're going to have some kind of system to lift this weight. Okay. And might be resistance in the pulleys or whatever. Okay, so you've got energy lost to the pulleys, and you've got energy lost to the internals of the motor actually lifting it. Okay, so your two reasons, and you just kind of explain them saying, well, therefore, not all the energy is going to be transferred to the lifting of the mass. Therefore, it's not going to reach the. Okay, so very similar explanations, but as I say, it's just two reasons why energy would be lost. Okay, although it says do not allow losses due to sound or air resistance. Okay, I don't know why, but apparently so. Okay, I think the fact that you can't mention air resistance because it's not moving fast enough, I think that's probably why it's mentioned that. But it does say you can't. So if you did put a max, an explanation for that, then you wouldn't get any marks at all. Okay, right. So that's the end of question 3. Not too bad. I think there's a few little points in there that you might tripped up on. I think the drawing of that second line would have been bit of a pain. But apart from that, I don't think it was too bad. Anyway, thanks for watching, and we'll see you in question 4.